Hello there, and a warm welcome to the Sleepy Science channel. I'm genuinely delighted you've found your way here. Perhaps the day has been a particularly long one, leaving you weary and in need of respite. Or perhaps you belong to that special breed of individual who, rather than counting sheep, finds solace in drifting off to sleep while pondering the mysteries of time, the relentless pull of gravity, and the profound, almost deafening silence that reigns supreme in the vast gulfs between galaxies. Whatever your reason for joining us, tonight's journey is tailored specifically for you. There's absolutely nothing you need to do now except simply rest. Allow your breath to slow its pace, your thoughts to soften and gently unfurl, and your body to grow quiet and still. Imagine yourself already floating far, far away from Earth, soaring beyond the familiar constellations and into the infinite expanse where space itself stretches and expands in every conceivable direction. Because tonight, we're embarking on a leisurely drift into the far, far future of the universe. We won't be taking a direct headlong plunge, but rather a slow, meandering journey through cosmic chapters, each revealing a different stage in the universe's long and intricate story. We'll witness the final gasps of dying stars, the slow fade of once brilliant galaxies, and finally the long, cold silence that may very well lie beyond them all. This is a story told not in dramatic endings, but in the subtle language of entropy, in the immense and ever-growing distances between objects, and in the quiet, almost imperceptible settling of all things towards a state of ultimate stillness. From the ghostly glow of black dwarf stars and the ethereal evaporation of black holes to the very concept of time itself losing its meaning and relevance. This is a journey into the profound and absolute stillness that patiently waits at the very edge of everything we know and can imagine. We'll proceed slowly, gently, allowing you to absorb each concept, each image, one sleepy thought at a time. And just before we truly begin our journey into the cosmos, if you find that these quiet explorations help you unwind and release the tension of the day, or if they provide you with a peaceful and meaningful way to end your day, I would be incredibly grateful if you would consider gently tapping the like button and subscribing to the channel. It helps others, perhaps equally weary and curious souls, find their way here too, one sleepy soul at a time. Now, let's truly begin. When we gaze up at the night sky, particularly on a clear night far from the distracting glow of city lights, it's easy to be lulled into a sense of permanence and stability. The stars shimmer in their familiar patterns, constellations etched across the darkness like ancient celestial maps. The moon, our constant companion, returns in its steady, predictable cycles, waxing and waning with dependable rhythm. But this stability, this sense of unchanging permanence, is ultimately an illusion, a trick of perspective caused by our limited human scale. On cosmic timescales spanning billions and even trillions of years, everything is in a constant state of motion, a slow and majestic dance across the stage of the universe. And this motion isn't just through space, it's also through time itself. The universe is not a static backdrop against which events unfold. It is a dynamic, evolving entity, aging and changing in ways that are both subtle and profound. And like any aging system, from a human being to a complex machine, it is slowly but inexorably changing in ways that we, with our ever-improving technology and understanding, can begin to measure and even predict with increasing accuracy. The most immediate and readily observable sign of this cosmic aging lies in the phenomenon known as the redshift of distant galaxies. As light travels across the vast gulfs of expanding space, its wavelength stretches, shifting it towards the red end of the spectrum, much like the sound of a siren lowers in pitch as an ambulance speeds away from you. This means that the farther a galaxy is from us, the more its light is redshifted, providing us with a crucial clue not just to its distance, but to its place in the timeline of the universe itself. Galaxies are not simply moving away from us through space. The very fabric of space between us is growing, expanding at an accelerating rate. And with this expansion comes a gradual cooling and dilution of the universe as a whole. This redshift, therefore, is not just a measurement of motion, but a whisper from the distant past, a faint echo of the universe's infancy. But it's also a powerful glimpse into the universe's far future, revealing the direction in which the cosmos is inexorably heading. Cosmic background radiation, often referred to as the CMB, is another gentle but persistent indicator of the universe's age and evolution. This ancient light, a relic left over from when the universe was a mere 380,000 years old, a blink of an eye in cosmic terms, now permeates the cosmos as a faint and almost imperceptible microwave hum. When it first emerged in the immediate aftermath of the Big Bang, this radiation glowed brightly with a temperature of thousands of degrees. Today, after billions of years of expansion and cooling, it has cooled to just a few degrees above absolute zero, the theoretical point at which all molecular motion ceases. And it continues to cool, ever so slowly, over the course of billions upon billions of years. This fading radiation tells us something simple, yet profoundly important. The universe is getting colder. The intense warmth of the Big Bang, the cataclysmic event that birthed everything we know, is still with us, but only as a faint echo, stretched thin and diluted by the relentless march of time. Stars, too, are aging, both individually and as a collective population within galaxies. Our own sun, for example, is currently about halfway through its main sequence lifespan, the stable period in a star's life. During this phase, it diligently fuses hydrogen into helium in its core, shining steadily and reliably for billions of years, providing the energy that sustains life on Earth. But stars, despite their seemingly endless energy output, are ultimately finite machines. They require fuel, a constant supply of hydrogen, to maintain their thermonuclear furnaces. And once that fuel begins to run out, the stars inevitably change, evolving into different and often more dramatic phases. It is the great in the Earth spiral elliptic. Some will all of the high energy and if we could, this is the what we as the eventual the lab the unit at the this energy entropy. But one the unit galaxy the unit no more stars will shine, no more planets will orbit, no more complex structures will form, no more machines, biological or mechanical, will be able to function. And yet, even in this final stillness, the entropy of the universe will be maximized. It is the quietest possible outcome, a cosmos not torn apart by some cataclysmic event or crushed by runaway gravity, but simply settled, having reached its ultimate state of equilibrium. Not dead in the dramatic sense, but just done, its potential for change exhausted. Not a sudden ending, but the slow and inevitable fulfillment of a long entropic journey. To truly understand how the universe might end, we must first stretch our imaginations across unimaginable spans of time, far beyond our everyday human experience. The current age of the universe is around 13.8 billion years, a number that already defies our intuition and challenges our ability to comprehend its vastness. But if the universe continues expanding as expected, driven by the mysterious force of dark energy, it could persist for hundreds of trillions, even quadrillions of years, an almost incomprehensible timescale. These durations are so long that all known stellar activity, all galactic mergers, and even the slow evaporation of black holes will take place relatively early in comparison, like fleeting moments in an eternal drama. Over the next few billion years, galaxies like our own will continue forming stars from the gas and dust that remains within them. But this fuel is finite, and the rate at which new stars are born is gradually decreasing. Star formation rates have already declined dramatically since the universe's peak period of stellar birth, which occurred about 10 billion years ago. In perhaps 100 trillion years, the last star will flicker into darkness, its thermonuclear furnace finally extinguished. What follows is what astrophysicists refer to as the degenerate era, a time when white dwarfs, neutron stars, and black holes drift silently through the vast emptiness of space, the ghostly remnants of a brighter cosmic past. As this era unfolds, these compact objects will slowly cool, gradually releasing their remaining thermal energy into the surrounding void. They will occasionally collide or interact gravitationally, but such events will be rare, exceptions to the general rule of stillness and isolation over even longer timescales, stretching into 10 to the power of 100 years or more. Even the fundamental building blocks of matter, protons, may decay, depending on the ultimate laws of particle physics. If proton decay is a real phenomenon, then all normal matter, atoms, planets, the remnants of stars, would eventually disintegrate into subatomic particles. A thin mist of radiation spread across the vastness of space. If not, matter will still decay in more exotic and subtle ways, through quantum tunneling and gravitational interactions, processes that are incredibly slow but ultimately inevitable over such immense timescales. The long, slow cooling of the universe, driven by the relentless increase in entropy, leads towards a concept known as heat death. This is not an explosive ending, a violent cataclysm, but a terminal settling, a final and irreversible state of equilibrium. In this scenario, the universe asymptotically approaches thermal equilibrium, its temperature becoming increasingly uniform across all scales. All temperature gradients flatten out, all usable energy is expended, and no stars shine. No structure changes, no new forms emerge, and no work is done. It's a state of maximum entropy, where the cosmos still contains energy, but none of it can be harnessed to create change, to drive new processes, or to sustain life. Everything continues, but nothing happens. This is one of the most widely accepted possibilities for the ultimate fate of the universe, a scenario supported by a vast body of observational evidence and theoretical understanding. Unlike a dramatic collapse or explosion, heat death is quiet, absolute, and eternal, a state of ultimate stillness. It is driven by the same fundamental laws of physics that govern why coffee cools in a mug or why stars eventually run out of fuel. But here, those same laws apply to everything, on every scale, for all of time. And while this outcome lies far beyond anything we can directly witness or experience, it follows directly from what we already observe in the sky, from the redshift of distant galaxies to the fading glow of the cosmic microwave background. So the next time you see a star twinkling brightly in the night sky, remember that it is burning fuel, creating order and complexity within itself at the cost of increasing entropy in the universe as a whole. It is a temporary flare of concentrated energy, a fleeting moment of complexity in a universe whose long-term direction is downward towards simplicity, stillness, and silence. This way, cosmic aging is not just about the passage of time. It is about the deep physics of how time works, about the fundamental laws that govern the universe and dictate its ultimate fate. And as we move forward on this journey, we will follow this story from stars to atoms, from galaxies to black holes, tracing each step towards the end, towards the quiet stillness that awaits us all. To understand the long future of the cosmos, we must first understand its luminous engines, the stars. Every star we see in the night sky is a complex thermonuclear furnace, a delicate and intricate system balancing the inward pull of gravity with the outward pressure of radiation generated by nuclear fusion in its core. This delicate balance defines a star's main sequence phase, the longest and most stable period in its life, where it spends the majority of its time fusing hydrogen into helium, releasing vast amounts of energy in the process. The Sun is currently in this phase, quietly and reliably burning through the fuel at its core, shining with the steady light of equilibrium, providing the energy that sustains life on Earth. Hydrogen fusion is the simplest and most efficient nuclear reaction in the universe, and it powers stars for billions of years, depending on their mass. Smaller stars burn fuel slowly, living for tens or even hundreds of billions of years. Larger stars are brighter and hotter, but live much shorter lives, racing through their hydrogen supplies in just a few million years. But no matter the size, all stars eventually face the same fate. They run out of fuel, and the balance that held them together begins to fail. As hydrogen becomes scarce in the core, the star's core contracts under the relentless pressure of gravity, heating up in the process. In many stars, this leads to a new phase, the red giant stage. The outer layers of the star swell outward, often expanding to immense proportions, sometimes even engulfing nearby planets, while the core continues to fuse heavier elements like helium and carbon, trying to stave off the inevitable collapse. This stage is unstable and temporary, a desperate attempt to maintain equilibrium. The star's structure becomes layered and dynamic, with fusion occurring in shells around an increasingly dense core. Eventually, even these fusion reactions can no longer continue, and the star's fate is sealed. The way a star dies depends entirely on its mass. Small to medium stars, like our Sun, shed their outer layers into space, creating glowing planetary nebulae, beautiful and intricate structures that are among the most visually stunning objects in the universe. The core that remains becomes a white dwarf, a dense object roughly the size of Earth, but with the mass of the Sun. These stellar remnants no longer undergo fusion, they simply glow faintly with leftover heat, slowly cooling over trillions of years until they become cold, invisible black dwarfs. No black dwarfs exist yet in the universe because not enough time has passed since the Big Bang for even the oldest white dwarfs to cool completely. Heavier stars, on the other hand, end their lives more violently. When fusion stops in a massive star's core, gravity wins completely. The collapse is sudden and catastrophic, resulting in a supernova, an explosion that can outshine an entire galaxy for a brief time, scattering heavy elements into the surrounding space. What remains after the blast depends on the original mass of the star. If it was heavy enough, the core becomes a neutron star, an object so dense that atomic nuclei are crushed into a sea of neutrons. These stars are only about 20-kilometer wide, yet they can weigh more than the Sun. In the most extreme cases, even neutron degeneracy, the force that prevents neutrons from collapsing further, cannot hold back gravity. The core collapses further, forming a black hole, a region of space-time where gravity is so intense that nothing, not even light, can escape. Black holes do not shine, they do not radiate, at least not in the traditional sense, but they persist, and they are now considered likely to be the last surviving structures in the universe, the ultimate repositories of matter and energy. From the soft starlight of a distant sun to the violent collapse of a supernova, the fate of every star sets the stage for what the universe becomes. Star formation is not an eternal process. It depends on the presence of cold hydrogen gas, the raw material that gravity condenses into new stars. Over cosmic time, galaxies have drawn from large reservoirs of interstellar gas to create generations of stars. But this supply is finite, and as stars form, they consume this fuel, locking away a portion of it permanently. Some of the material is returned to the interstellar medium through supernova explosions and stellar winds, but not enough to replenish what was consumed. Slowly, over billions of years, the galaxies are running dry, their reservoirs of hydrogen gas dwindling. Already the universe is well past its peak in stellar birth. That peak occurred more than 10 billion years ago. Since then, the rate of star formation has declined by more than 90%. Large galaxies like the Milky Way still form stars, but more slowly than in the past. Smaller galaxies and gas-poor systems are nearly dormant, their star-forming days long gone. Eventually, perhaps within 100 trillion years, the last of the interstellar hydrogen will be gone, and the final star will be born. After that, the universe enters a new phase, a dark and silent era unlike anything that came before. This future era, sometimes called the degenerate era, will be one of deepening stillness. No new stars will flicker to life, no bright blue giants or gentle yellow suns will form. Only the remnants of what once was will remain: white dwarfs, neutron stars, and black holes. These objects will continue to drift through the darkening void, occasionally interacting but mostly traveling alone, the solitary survivors of a cosmic drama that has long since ended. Great stellar cities, galaxies will persist in form but no longer in light. Their spark will be gone, their brilliance faded into the blackness of space. Among these remnants, white dwarfs will be the most numerous. These dense, inert stellar cores no longer fuse atoms. They shine only because of residual heat, leftover thermal energy from their former lives. But this heat, too, will fade. Over trillions and quadrillions of years, white dwarfs will cool, growing dimmer and redder, eventually radiating only in infrared. In time, they will become entirely dark, invisible to even the most sensitive detectors, cold and silent tombs drifting through the void. These fully cooled objects are called black dwarfs. No black dwarfs exist yet. The universe is simply too young. Even the oldest white dwarfs have only had around 13 billion years to cool, not nearly enough time to reach the cold, lightless state of a black dwarf. But in the far future, these dark remnants will dominate the cosmos, outnumbering all other objects and representing the final stage in the life cycle of most stars. No longer stars themselves, but the silent memories of stars, each one carrying a history of thermonuclear fire now extinguished, their matter frozen in slow, dense silence. This transition marks a major turning point in the universe's story. Most of its life so far, the cosmos has been lit by starlight, the quiet, ongoing burn of hydrogen into helium. That era is temporary, a brief and fleeting moment in the grand scheme of things. As the fuel runs out, so too does the light. The skies will go dark, not because something failed, but because the firewood was finite. And once the last embers fade, the universe enters a long night, not empty, but deeply still. The universe still contains a vast number of stars, roughly 100 billion in our galaxy alone, and likely more than 100 billion galaxies in the observable cosmos. But even this abundance is a snapshot in time, a fleeting glimpse of a universe at its peak of star formation, represents only a moment during the star-rich epoch of the universe, a brief window of brilliance in the long history of the cosmos. In the far future, this light will fade and the universe will become a much darker and quieter place. According to current models, the last visible stars will burn out roughly 100 trillion years from now, a number that dwarfs the current age of the universe by a factor of more than 7,000. These final stars will not be brilliant giants or blue-eyed beacons. They will be red dwarfs, the smallest and longest-lived stars. Like their more massive cousins, red dwarfs burn their hydrogen fuel extremely slowly and do so in a fully convective manner, meaning nearly all of their mass contributes to fusion. Some may live for tens of trillions of years, slowly and steadily releasing their energy into the void. But even these cosmic slow burners are bound by the laws of thermodynamics. Their fuel will eventually run out, and when it does, they will fade gently into darkness, their light extinguished forever. After the last red dwarf cools, the universe will no longer produce visible light. For the first time since stars began to form, there will be no starlight shining anywhere, no new energy being generated to illuminate the cosmos. The night sky will become permanently dark to the human eye. Only faint glows in infrared or radio may persist, and only briefly on cosmic scales. There will be no more sunrises, no constellations to guide sailors across the seas, no glowing galaxies to inspire awe and wonder. The visual richness of the universe, which has shaped life and guided cultures for billions of years, will vanish entirely, replaced by an eternal darkness. But this darkness is not emptiness. It is simply the absence of new light. The universe will still contain matter, black dwarfs, neutron stars, black holes, rogue planets, and drifting debris, all scattered sparsely across an ever-expanding sea of space. These objects will interact occasionally, perhaps merging or falling into black holes, but most will continue in isolation, following the slow gravitational dance of a cosmos that no longer shines. Will be a universe of memory, not creation, a place where the echoes of a brighter past reverberate through the void. In this quiet era, time will take on a different character. Without bright stars to mark days, years, or centuries, the passage of time becomes nearly imperceptible. Cosmic events will unfold not over millions of years, but over trillions and quadrillions, timescales that are almost impossible for the human mind to grasp. Change will still happen, but so slowly that entire galaxies could drift without incident for longer than the current age of the universe multiplied by 1,000. It is not that time stops, only that activity stretches so thin as to seem eternal, a universe moving so slowly that it appears to be frozen in time. And so the sky, once filled with brilliant constellations and pulsing nebulae, will grow quiet, not suddenly, but gradually, star by star, light by light. It will become a true night sky with no dawn to follow, an eternal darkness unbroken by the arrival of a new day. This is not a disaster or a collapse. It is simply the cooling of a once bright system, the gentle exhale of a universe that spent its energy well, a natural and inevitable process dictated by the laws of physics. And with this final stillness, we move one step closer to understanding what lies at the end of everything, to grasping the ultimate fate of the cosmos. The stars may fade, but matter, the atoms and particles that make up everything, does not simply vanish with them. Once the last lights go out, what remains is not nothingness, but structure. The durable remnants of atoms, compressed cores of stars, and drifting cosmic debris, all the building blocks of a universe that once teemed with energy and activity. And yet even matter itself may not be eternal. Over long enough timescales, the very stability of the proton, one of the universe's most fundamental building blocks, comes into question. Protons are stable on timescales far longer than the age of the universe. We have never directly observed a proton decay. In fact, if protons do decay, their half-life must be at least 10 to the power of 34 years, more than 100 trillion years. But some grand unified theories of particle physics predict that protons are not immortal. They may eventually break down into lighter particles such as positrons and neutrinos through rare quantum processes. This decay, if real, would mark a turning point for matter, a fundamental shift in the composition of the universe. If protons decay, then every atom in the universe is doomed to disintegrate given enough time. Atoms are built around protons and neutrons, which form their nuclei. Electrons orbit these nuclei, held in place by electric charge. But once the proton disappears, the atom unravels. Molecules lose coherence, structures dissolve, and the cold solid remnants of long-dead stars would eventually fall apart into a thin mist of radiation and light particles, drifting alone through the dark. This process would be extraordinarily slow. In the early stages of the degenerate era, matter would still appear solid and unchanging, but as trillions upon trillions of years pass, individual protons would begin to decay like grains of sand slipping through an hourglass. Entire white dwarfs and neutron stars, once seemingly eternal, would crumble into radiation, their dense cores dissolving into nothingness. Even planets and interstellar debris would disintegrate, their atoms slowly unraveling. It would not be sudden nor dramatic, just a slow thinning of matter, an unraveling of everything once built, a gradual return to the fundamental particles from which it all began. But what if protons do not decay? Then matter, at least in its degenerate forms, may persist indefinitely. Atoms would remain bound even if they no longer participate in chemistry or energy exchange. White dwarfs and neutron stars might remain frozen and inert, lasting into eternity, their dense cores resistant to all forms of decay. The decay of structure would be limited not by particle instability, but by rare quantum events like tunneling or collisions, incredibly unlikely events that could still disrupt the stability of matter over vast stretches of time. Even so, the universe inexorably sheds its structures one by one. There is no cosmic reset button, no second act featuring the birth of new stars or the formation of nascent galaxies. The very though even as star in new these it pos in a new these over but in the these new they shed something one of them in the these even if a black it is these would for the most whether what the grand black hole as but even proposed by the brilliant physicist Stephen Hawking in the 1970s. This mechanism arises from the complex interplay of quantum fluctuations near the event horizon, the point of no return beyond which nothing can escape the black hole's grip. Seemingly empty space, particle-antiparticle pairs are constantly popping into and out of existence. Near a black hole, one of these particles may fall into the singularity, while its partner escapes into the surrounding universe. To an external observer, it appears as though the black hole is emitting radiation. This process, while undeniably real, is incredibly slow. It means that black holes lose mass over vast stretches of time, gradually shrinking until they eventually vanish completely. For a black hole with a mass comparable to our Sun, this evaporation process would take on the order of 10 to the power of 67 years, far longer than the time required for stars to die or matter to decay. For supermassive black holes residing at the centers of galaxies, these timescales stretch even further, reaching 10 to the power of 100 years or more. But given sufficient time, even the most massive black holes will eventually fade away. In their final moments, they will release a brief, spectacular burst of high-energy radiation before disappearing entirely, leaving behind only the altered curvature of space-time. This may very well be the last visible event in the entire history of the universe. What follows this final disappearance is something far deeper and more profound than mere darkness. It is not simply the absence of stars or even the absence of matter. It is the absence of structure itself. A universe devoid of black holes is a universe without concentrated gravitational centers, no points of extreme density, no organized formations, no discernible edges. All that ultimately remains is the physical vacuum, a space that is not truly empty, but instead filled with the lowest possible energy state permitted by quantum fields. This vacuum state is uniform, isotropic, meaning it looks the same in all directions, and incredibly quiet. Even this apparent nothingness is not nothing in the strictest sense. The vacuum possesses inherent properties. It contains virtual particles that flicker in and out of existence. It possesses a ground state energy. It can even influence the expansion of space through phenomena like dark energy, but it contains no usable energy, no gradients, no change. It represents a stillness so profound that it supports existence without requiring any activity. Philosophically, this challenges our fundamental notions of what it truly means for something to be. In physics, it represents the end state of all processes, not a place, but a condition. And so, after the last black hole evaporates in a final burst of radiation, the universe transforms into a vast sea of near-perfect emptiness. No stars, no atoms, no discernible motion, only fundamental particles and residual radiation spread thinly across an endless, ever-expanding void. The matter that once formed planets, people, and majestic galaxies is now irrevocably dissolved, disassembled, and utterly untraceable. The stage, the arena of cosmic events remains, but the play has definitively ended. What was once dynamic and vibrant has succumbed to an all-encompassing quietude. And in this profound stillness, the long, strange fate of matter reaches its final, inevitable chapter. Not destruction, but dispersal into an eternal silence. Black holes, paradoxically, begin their lives as endings. They are forged from the cataclysmic collapse of massive stars, a process where gravity overwhelms all other forces, compressing matter into a singularity, a point of infinite density. This core collapse heralds the death of the star, its transformation from a luminous beacon into an invisible enigma. But for the nascent black hole, this is merely the beginning of its own strange and protracted existence. Black holes themselves do not shine, but they possess the remarkable ability to grow, accreting matter from their surroundings. Given a sufficient supply of fuel, they can evolve into the most massive single objects in the entire universe, and through their relentless growth, they profoundly shape the destinies of the galaxies within which they reside. The primary mechanism by which black holes grow is through accretion, the slow, steady consumption of nearby gas, dust, and even entire stars. As matter spirals inward towards the black hole, it forms a swirling accretion disk, a superheated maelstrom of particles that emit intense radiation before ultimately crossing the event horizon. In the early universe, black holes had relatively easy access to fuel. Galaxies were denser and more turbulent, richer in gas and cosmic dust. Supermassive black holes, typically found lurking at the very centers of galaxies, grew rapidly during these chaotic epochs, sometimes reaching billions of times the mass of our Sun within a few 100 million years. Mergers between galaxies offer another pathway to growth for black holes. When galaxies collide, a relatively common occurrence in the grand tapestry of cosmic history, their central black holes often engage in a complex gravitational dance, spiraling towards one another until they eventually coalesce into a single, even more massive black hole. These black hole mergers release immense amounts of energy in the form of gravitational waves, ripples in the fabric of space-time that carry away energy and momentum, allowing the two singularities to finally merge into one. Over vast stretches of time, this process leads to a gradual consolidation of gravitational structure, creating fewer but substantially more massive black holes. Each merger reduces the overall number of black holes in the universe, but simultaneously increases their average mass. Yet even this relentless growth is ultimately limited. As the universe continues to expand and galaxies drift farther apart, the opportunities for both mergers and accretion steadily diminish. The readily available supply of infalling matter dwindles. Stars drift too far away to be captured by the black hole's gravitational pull. Gas becomes too diffuse to form a substantial accretion disk. Eventually, most black holes will become gravitationally isolated, no longer active participants in the dynamic evolution of galactic cores, but instead drifting alone through the vast, empty darkness of intergalactic space. This era of black hole starvation marks a profound transition from the active, luminous cosmos of the past to the silent, enduring universe of the far future. The vibrant accretion disks vanish, the gravitational encounters cease. Black holes, once voracious consumers of matter, become largely inert, simply existing as massive concentrations of gravity. They persist because there is little to actively challenge them, but they also fade from the cosmic stage, playing no further role in the creation of new light, new stars, or new complex structures. They become silent witnesses to a universe that is slowly, inexorably running out of fuel, and so the black holes that once shaped galaxies and bent the orbits of stars will ultimately drift alone. For trillions upon trillions of years, they may remain undisturbed, massive, dark, and patient, the last large-scale structures left intact long after the galaxies have dimmed and the stars have died. But even their profound stillness is ultimately temporary. A deeper, more fundamental process is patiently waiting, governed not by the familiar forces of gravity, but by the strange and often counterintuitive laws of quantum mechanics. And it is through this quantum process that even black holes, those seemingly eternal objects, must eventually fade into oblivion. The silence surrounding an isolated black hole may appear to be absolute and final, but it subtly conceals a quiet process unfolding at the very edge of our understanding of physics. Even in perfect darkness, a black hole is not completely still. It radiates faintly, invisibly, and incredibly slowly through the aforementioned process known as Hawking radiation. Though black holes, by definition, trap everything that crosses their event horizon, quantum mechanics dictates that no region of space can ever be truly empty. The vacuum near the event horizon, virtual particles continuously flicker into and out of existence, appearing and disappearing in a fleeting dance governed by quantum probabilities. Occasionally, one of these virtual particles manages to escape the black hole's gravitational grasp, while its partner falls into the singularity. From the perspective of an outside observer, it appears as though the black hole has emitted a real particle, and in doing so has lost a tiny, almost imperceptible amount of mass. This subtle process, known as Hawking radiation, occurs for all black holes, regardless of their size. However, the rate at which a black hole radiates is inversely proportional to its mass. In simpler terms, the larger the black hole, the slower it radiates away its mass. For a black hole with a mass comparable to that of our Sun, the rate of Hawking radiation is so negligible that it is practically undetectable. For a supermassive black hole, the rate is even closer to zero. Still, Hawking radiation never fully ceases. Given enough time, far, far longer than the current age of the universe itself, even the most massive black holes will eventually shrink, imperceptibly at first due to the gradual loss of mass through this quantum process. The process begins imperceptibly, unfolding over durations that exceed 10 to the power of 100 years, a timescale that defies our intuitive understanding of time. During this initial period, black holes remain largely massive and stable, but the slow, steady leak of quantum particles continues unabated. They lose energy bit by bit, their mass gradually reducing at a pace so slow that it utterly escapes all current methods of detection. However, as black holes shrink, the process accelerates. Near the very end of a black hole's extraordinarily long life, its mass becomes small enough that the rate of Hawking radiation increases rapidly. Its final moments, the black hole releases a burst of high-energy particles, gamma rays, electrons, neutrinos, a final whisper of energy before vanishing completely. No tangible trace is left behind. The event horizon disappears, and the highly curved region of space-time that it defined returns to the relatively flat geometry of the surrounding vacuum. This final disappearance represents more than simply the end of an object. It signifies the loss of the last gravitational anchors in the universe. Black holes are the most concentrated sources of mass and gravity in existence. Their immense gravitational pull organizes and shapes the space around them. When they evaporate, that organizing influence fades. The cosmos becomes flatter, less curved, and more uniform. Without stars, without galaxies, and now without black holes, the large-scale structure of the universe ultimately dissolves into a sea of weakly interacting particles, spread thinly across an unimaginable expanse. This way, black hole evaporation is not only the end of a specific object, but also the end of the very concept of shape and form within the universe. It signals the conclusion of curvature, mass, and structure, leaving behind only the uniform and featureless vacuum. What was once a dynamic cosmos filled with deep gravitational wells and luminous objects transforms into a vast, nearly empty field. Space no longer clings to anything. Time continues to pass, but it has nothing upon which to act. The last traces of organized mass are gone. What remains is emptiness, deep, wide, and quiet, beyond the capacity of human imagination. As black holes evaporate, a profound and unsettling question emerges, one that touches the very core of physics itself. What ultimately happens to the information that fell inside the black hole? According to the fundamental principles of quantum mechanics, information about a closed physical system can never be completely and irrevocably lost. Yet black holes seem to do precisely that. Anything that crosses the event horizon becomes permanently inaccessible to the outside universe. When the black hole eventually evaporates through Hawking radiation, the information it once held appears to vanish, seemingly defying the fundamental rules of quantum theory. This is the heart of the black hole information paradox, a problem that has captivated and perplexed physicists for decades. Some propose that information is somehow encoded within the Hawking radiation itself, spread out in subtle patterns that are currently too complex to detect. Others suggest that information may be stored in complex correlations at the event horizon, a concept known as the holographic principle, which posits that all the information contained within a volume of space can be represented on its boundary. There are even more radical ideas, such as the possibility that black holes retain a tiny Planck-scale remnant where information could be preserved indefinitely. But to date, no single resolution has been universally accepted, and the black hole information paradox remains one of the great unsolved mysteries in theoretical physics. Thermodynamics adds yet another layer of complexity and mystery to the puzzle. Black holes possess entropy, a measure of disorder that is directly proportional to the surface area of their event horizons. They also possess temperature, which is the underlying basis of Hawking radiation. As black holes evaporate, their entropy steadily decreases, which seems to contradict the second law of thermodynamics, which states that the total entropy of a closed system can never decrease over time. However, if the outgoing Hawking radiation carries away not only energy but also entropy and potentially information as well, then the second law may still hold true. Understanding how thermodynamics and quantum mechanics coexist and interact at the event horizon of a black hole could hold the key to unlocking a deeper, more unified theory of everything, a theoretical framework that reconciles all the fundamental forces of nature into a single, elegant description of the universe. When the last black hole finally dies, the universe enters a new and profoundly different phase, one devoid of complex structure. No gravitational centers remain, no ongoing fusion reactions, no gravitational collapse, no organized matter, only a vast and ever-thinning sea of radiation, neutrinos, and other fundamental particles dispersed across incomprehensible distances. These particles, for the most part, do not interact meaningfully with one another. They simply drift, separated by vast expanses of increasingly cold and empty space. The cosmos has no discernible gradients, no engines to drive change, no source of light. It becomes a diffuse, ghostly echo of its former, vibrant self. In this state, the universe is as close to thermodynamic equilibrium as it can ever get. Entropy is maximized, disorder reigns supreme, and temperature is essentially uniform throughout. The vacuum energy that drives the continued cosmic expansion remains, but there are no systems left to be powered by it. There is no meaningful time in the human sense, no change, no significant motion, no functioning clocks. The arrow of time still points relentlessly forward, but it moves through a state of perfect stillness. The cosmos continues to expand, not into anything, but simply becoming more dilute, more evenly distributed, and more profoundly flat. And what ultimately remains after all this? Possibly nothing but fundamental quantum fields stretched thin across the vastness of space. Perhaps a few hardy particles that stubbornly resist all forms of decay, perhaps a background of extremely faint radiation, so diffuse that it can never be harnessed, or perhaps simply the vacuum itself, the most minimal version of existence imaginable, remains as the ultimate and final canvas. It is not an end marked by a bang or even a sigh. It is a settling into something that cannot age because it can no longer change. A place where the universe, having spent its vast reserves of energy, finally finds a state of eternal rest. Even as matter fades into the background and black holes vanish from existence, space itself continues to evolve. The universe is not expanding into something. Rather, it is space itself that is stretching, growing, and thinning with each passing moment. This expansion has been ongoing since the Big Bang, the moment of the universe's birth. However, it has not been uniform in its rate of expansion. For the first few billion years after the Big Bang, gravity acted as a brake, slowing the expansion and pulling matter together to form galaxies and other large-scale structures. Then, something changed. Approximately 5 billion years ago, the expansion of the universe began to accelerate, driven by a mysterious force known as dark energy. Dark energy is not yet fully understood by physicists, but its effects are readily observable. It acts as a repulsive pressure, causing galaxies to move away from one another at an ever-increasing rate. The more space there is in the universe, the more dark energy seems to emerge, accelerating the expansion process even further. Like gravity, which pulls objects together, dark energy relentlessly stretches them apart. As a direct result of this accelerated expansion, the large-scale structure of the universe is becoming increasingly diffuse. Galaxies that are currently visible from Earth will soon recede beyond our ability to detect them, their light redshifted to such long wavelengths that it becomes undetectable by any conceivable instrument. This leads to the concept of a cosmic event horizon, a boundary beyond which light will never reach us, no matter how long we wait or how advanced our technology becomes. As space expands faster than light can travel, entire regions of the universe will effectively slip away from us forever, becoming inaccessible to any future observation. These galaxies are not physically moving through space faster than the speed of light. Rather, the space between us and them is expanding so rapidly that no signal, not even light, can bridge the ever-widening gap. In the far future, only a small handful of neighboring galaxies will remain visible from our vantage point in the Milky Way. Everything else will fade into an undetectable silence, lost to the accelerating expansion of the cosmos. As the expansion continues unabated, this cosmic event horizon will grow more and more profound. Eventually, even within our own local region of space, the distances between objects will stretch so dramatically that any form of communication or interaction will become virtually impossible. Stars, black holes, and fundamental particles will still exist, but they will be increasingly isolated by the sheer scale of the surrounding space. Every point in the universe will effectively become an island, surrounded by a vast ocean of vacuum that no ship of light can ever hope to cross. The Hubble constant, a parameter that describes the current rate of expansion of the universe, may not remain constant forever. Some theoretical models suggest that the Hubble constant could stabilize at some point in the distant future, while others allow for it to continue to evolve over time, potentially even increasing its rate of expansion. If dark energy is indeed a cosmological constant, a fixed and unchanging energy density of the vacuum itself, then the expansion will proceed steadily and inexorably into the infinite future. However, if dark energy is something more dynamic, such as a slowly changing quantum field, then the future could hold unforeseen surprises. Still, all astronomical observations to date strongly point towards a continued acceleration of the cosmic expansion. The universe is not just growing in size, it is racing outward faster and faster with each passing moment, driven by the mysterious and unrelenting force of dark energy. This relentless stretching does not currently tear objects apart, at least not yet. Galaxies, stars, and atoms remain bound together by the cohesive forces of gravity and the strong nuclear force. However, on the largest scales, space-time itself is effectively uncoupling from itself. The formation of new large-scale structures has effectively ceased. Gravity is no longer able to effectively clump matter together to form new stars and galaxies. The overall expansion is not chaotic or turbulent, it is a smooth, steady, and remarkably quiet process. It represents a transformation not of the contents of the universe, but of its overall context. The very canvas of the universe is being pulled wider and wider with each passing moment, driven by the unrelenting force of dark energy. The expansion of the universe is often described using a quantity called the scale factor, a dimensionless number that represents the relative size of the universe at any given time. This is essentially a measure of how distances between unbound objects in the universe change over time. When the scale factor doubles, all intergalactic distances have doubled. Since the Big Bang, the scale factor has grown enormously, and under the influence of dark energy, it is increasing faster with each passing epoch. This relentless growth doesn't add any new matter or energy to the universe. Instead, it spreads what already exists across an ever larger stage. As the scale factor grows, everything that is not gravitationally bound together becomes more remote from everything else. Galaxies that once shared causal contact, meaning that they were able to exchange information with one another, now drift too far apart to exchange even a single photon. The rate at which space expands between these regions now far outpaces the speed of light. This does not mean that matter is physically moving through space faster than the speed of light. Rather, it is space itself that is stretching over time, carrying galaxies along with it. The observable universe, the sphere of everything that we can potentially detect from Earth, is effectively shrinking, not in actual physical size, but in terms of its meaningful content. Less and less of the cosmos remains directly accessible to our observations. The implications of this are subtle but profound. When the observable universe was young, it contained nearly the entirety of the cosmos. Today, a significant fraction of what exists has already moved beyond our event horizon, becoming permanently inaccessible to our telescopes. The far future, any observers that remain will only be able to see the closest remnants of cosmic structure. To them, the universe will appear static, dark, and overwhelmingly local. The signs of expansion will be erased from view, not because the expansion has stopped, but because those distant regions have receded beyond the boundaries of visibility. This process ultimately leads to what physicists refer to as flatness. As matter thins out and large-scale structures fade away, the overall geometry of the universe approaches perfect uniformity. Space becomes smoother, more isotropic, and less warped by the presence of mass and energy. Without the large-scale gravitational distortions caused by galaxies and black holes, the curvature of space-time flattens out. The dynamic fabric of the cosmos gradually settles into a state of pristine simplicity. Every region of space effectively becomes like every other region, not identical in detail, but indistinguishable in terms of its overall behavior. The universe loses contrast, becoming a vast, empty, and ultimately symmetrical expanse. At this point, the rate of change itself slows dramatically. There are no new stars forming, no significant structures evolving, no visible interactions occurring. The remaining fundamental particles continue to move through space, but their paths are largely unaffected by one another. Entropy has effectively erased the sharp defining features of the universe. What was once a turbulent dance of gravity and radiation ultimately transforms into a tranquil drift through an infinite emptiness, a state of cosmic inertia. This is not because time has stopped flowing, but because nothing remains to mark its passing. And so the universe becomes quiet, not just in terms of light and motion, but also in terms of curvature. The great stretches of space-time that were once warped and distorted by galaxies and black holes now lie nearly undisturbed. The stage of the cosmos is still present, but its players have long since departed. What ultimately remains is the framework of the universe itself, expanding, stretching, and smoothing into an ultimate state of simplicity. As we move forward, we will explore what this final geometry might actually look like, and whether even space-time at its ultimate limit has a fate of its own. As the universe expands and empties, it moves closer and closer to a state known in cosmology as de Sitter space. This is a theoretical solution to Einstein's field equations, a model of a universe that is dominated entirely by vacuum energy, where matter and radiation are virtually absent and space expands exponentially forever. Sitter space is exceptionally smooth, perfectly symmetrical, and virtually featureless. It is not a region of destruction or annihilation, but rather a region of infinite stillness, a kind of cosmic plateau beyond which any meaningful change becomes impossible. In de Sitter space, the expansion is not chaotic or unstable. It is perfectly uniform and seemingly unending. Every region of space grows at the same exponential rate. From any given point within de Sitter space, the universe will appear to have a horizon, a boundary beyond which light will never be able to reach the observer. However, this boundary is not a physical edge of the universe. It is simply a consequence of the accelerated expansion. Like standing in a fog so dense it seems to solidify with every meter you advance, the cosmic horizon isn't a product of some physical barrier. There's no obstruction, no wall at the edge of the universe. Instead, it's a consequence of the relentless expansion, a cosmic race where the fabric of space-time forever outpaces the fastest signals we can send. The universe, in essence, is stretching faster than information can travel across it. Even within the seemingly pristine, smooth geometry of de Sitter space, the fundamental laws of thermodynamics stubbornly hold their ground. This space possesses an associated temperature and entropy, albeit infinitesimally low, a whisper of heat in an otherwise absolute zero. Crucially, the horizon that arises within this accelerating universe is not devoid of properties. It carries entropy, a measure of the information irretrievably hidden beyond its reach. This entropy, however, is finite, a fixed quantity dictated by the value of the cosmological constant. This suggests a profound limitation. Even the seemingly empty vacuum of space has a thermodynamic ceiling, a maximum number of possible quantum states it can contain. Once this ceiling is reached, once every possible configuration is exhausted, no further change, no further evolution is possible. This limit introduces a kind of heat death, but not just of matter, of space-time itself. In the traditional model of heat death, particles become evenly distributed, energy gradients vanish, and the universe becomes a homogeneous soup incapable of supporting change. In de Sitter space, this principle extends to the very geometry of the cosmos. The curvature of space becomes immutable, frozen. The expansion continues, yes, but it no longer carries information, no longer fosters the emergence of new structures, becomes pure, unadulterated background, a space-time that exists but utterly fails to do. Quantum fluctuations might still flicker into existence within de Sitter space, fleeting sparks of virtual particles popping into and out of reality, but these are random, unstructured, lacking any persistence. The vacuum may occasionally twitch, creating ephemeral bursts of energy, but with no gravity to bind these particles, no structures to anchor them, these fluctuations remain impotent, incapable of building anything lasting. The horizon, that implacable barrier, prevents coordination, while the entropy limit stifles any spark of novelty. The universe hasn't ceased to exist, it persists, a vast, empty stage, but it has lost the ability to express itself, to sculpt new forms, to write new chapters in its cosmic narrative. This is the ultimate destination of the cosmic arrow of time, not a singularity or a violent collapse, but an inexorable approach to a stillness so profound that even the very fabric of space-time ceases to evolve. The future collapses into an endless, unchanging present. Equations of physics still hold, but they describe a universe that has exhausted its potential, a universe that has simply run out of stories to tell. And as we gaze toward the final steps of this cosmic journey, we are compelled to ask a fundamental question. What happens when time itself no longer has a reason to pass? Time, as we understand it, is intrinsically linked to change. We perceive its passage by observing events, a star igniting, a planet orbiting, a particle decaying. These transitions mark the forward march of existence, the unfolding of reality. But as the universe becomes increasingly empty and still, the number of such transitions relentlessly dwindles. The far reaches of de Sitter space, change becomes so infrequent, so devoid of meaning, that time itself begins to dissolve as a useful concept. It's not that time stops, ceases to flow, but that it no longer measures anything of consequence. In everyday physics, time is a coordinate, an integral part of the fabric of space-time. It allows us to order events, to calculate durations, to understand cause and effect. But when events vanish, when no clocks tick, when no systems evolve, the difference between one moment and the next becomes purely abstract, a mathematical construct devoid of experiential content. If nothing changes between now and a trillion years from now, is there truly a difference? The mathematical arrow of time may persist, a ghostly echo of a bygone era, but its experiential resonance fades into oblivion. This raises profound questions, not just in physics, but in the realm of philosophy. In thermodynamics, the arrow of time is inextricably linked to entropy, the relentless drift from order to disorder. But in the ultimate heat death, entropy is already maximized. There are no more gradients, no more energy flows, no more distinctions. Entropy remains constant, and so does everything else. Without entropy change, time loses its thermodynamic direction, its fundamental asymmetry. The universe is not cycling, not collapsing, not undergoing any transformative process. It is simply existing, suspended in a single, vast, static state. In general relativity, time can bend, stretch, even loop under extreme conditions, creating wormholes and closed time-like curves. But in de Sitter space, these exotic possibilities fade away. The geometry of the universe becomes fixed, immutable. Expansion continues, an endless, monotonous stretching, but nothing actually happens within it. There are no clocks to measure time, no observers to experience its passage, no reference points to define its flow. Every location becomes indistinguishable from every other. Time continues to be defined mathematically, a parameter in an equation, but it loses its physical significance, its connection to the tangible reality. It becomes a variable with no terms left to evaluate, a symbol devoid of meaning. Some theorists speculate that in this ultimate limit, time may effectively evaporate from the physical description of reality. If no interactions remain, if no observers exist to mark its passage, then the very concept of time may become unnecessary, perhaps even meaningless. The universe wouldn't end in a catastrophic destruction, but in an absolute eternal silence. It wouldn't be frozen because freezing implies motion halted. Instead, it would be empty, a condition so stable, so perfectly balanced that nothing remains to distinguish one moment from the next. And so the end of space-time is not an event, a cataclysmic moment of destruction, but a horizon of stillness, a limit beyond which change is impossible. The universe does not crash into a wall, does not collapse into itself, does not undergo any dramatic transformation. It simply loses the capacity to evolve, to create, to become anything other than what it is. Expansion continues indefinitely, an eternal stretching of nothingness, but it carries no change, no energy, no future. The fabric of space-time remains, but the intricate pattern woven upon it fades into oblivion. It's a kind of immortality without memory, without history, without story. A cosmos that has reached the furthest edge of becoming and now simply is, existing in a state of perpetual, unchanging equilibrium. The very idea of the universe reaching a final, changeless state invites an even deeper, more unsettling question. Can space and time ever truly end? If nothing changes, does the fabric of space-time continue to exist? A silent, empty stage upon which no play will ever be performed again? Or is there a deeper boundary, not of space, but of meaning, beyond which the very concept of existence dissolves into incoherence? Physicists tread carefully here, venturing into realms where the tools of science, based on observation and measurement, become increasingly inadequate. A perfectly still cosmos, devoid of change, offers nothing new to observe, nothing to measure, nothing to analyze. In classical cosmology, space and time were often assumed to be eternal backdrops, immutable arenas that host events but are not events themselves. Yet modern physics increasingly views space-time as emergent, a property that arises from more fundamental relationships such as quantum entanglement or thermodynamic structure. If that's the case, then when those relationships vanish, when the underlying structures dissolve, the fabric they create may vanish too. Space-time may not persist in the absence of structure. It may not be a container, but a consequence, a derivative. Even the emptiest vacuum is not truly nothing. It is a quantum field in its lowest energy state, filled with virtual fluctuations and inherent uncertainty. These subtle features give rise to gravity, mass, and the fundamental forces of nature. If the vacuum loses this structure, if it settles into a truly minimal configuration, a state of perfect nothingness, then it is possible that the very geometry of space-time becomes undefined, loses its meaning. Without curvature, without particles, without fields in motion, there may be no meaningful coordinates to define position, no relationships to measure distance, no distinctions to mark the passage of time. The universe wouldn't collapse in a fiery implosion but fade into mathematical invisibility, a ghost in its own machine. This leads us to the speculative frontiers of physics, where our current understanding breaks down and new possibilities, however strange, must be considered. Could the universe tunnel into a deeper vacuum state, a more stable configuration of nothingness? Could time itself fragment, shatter into multiple dimensions, or emerge anew under exotic boundary conditions? Or could there be a transition, not to a new cosmos, but to a deeper silence, a place where the very grammar of physical law no longer applies, where the rules of the universe become meaningless? We simply do not know. Best theories break down in this regime, unable to provide definitive answers. In this context, the edge of time may not be a moment, a specific instant in the future, but a conceptual threshold, a limit to our understanding. Philosophically, this resonates with ancient questions about the void. Is emptiness a thing, a fundamental entity, or simply the absence of things, the lack of all definition? Is it a canvas upon which reality is painted, or simply the lack of canvas itself? The deep future, the universe may answer this question not with violence or cataclysm, but with a profound, all-encompassing stillness. If no observers remain, if no structure persists, the distinction between space and nothingness may blur, becoming indistinguishable. There may still be a mathematical universe, a set of coordinates and rules governing its behavior, but nothing within them to play the game, no players, no board, no purpose. In this way, the fate of space-time may not be destruction, but erasure, not by force, but by fulfillment, by the complete exhaustion of all possibilities. The cosmos may approach a kind of completion, a state where no further change is possible, and so no further physics is needed. Whether this is an end or a beginning depends on what follows, if anything. But in terms of the universe we know, built from fields and forces, space-time and motion, this would be the quietest end of all, a whimper rather than a bang. In the silence that follows the universe's final acts, a strange kind of possibility remains, not because of what is present, but because of what is absent. When the universe becomes flat, empty, and still, when it reaches maximum entropy and minimum structure, we are left with a question that stretches beyond the boundaries of physics, a question that touches upon the very nature of existence. Is this truly the end, the final curtain call, or simply the quiet before something new begins? With no matter to interact, no clocks to measure time, and no observers to witness its unfolding, the universe has no script, no predetermined destiny, but it may still hold potential, a latent capacity for something unforeseen. Some theorists suggest that even in the most silent vacuum, devoid of all activity, quantum fluctuations could still trigger new beginnings, seeding new realities in the ruins of the old. Tiny pockets of space could spontaneously tunnel into lower energy configurations, forming what physicists call bubble universes. These bubbles would expand from a single point, inflating into entirely new realms of physics, causality, and time, universes with laws and constants entirely different from our own. Our own universe may have begun in precisely this way, a spontaneous fluctuation in a prior vacuum, driven by conditions we cannot observe, governed by rules we cannot comprehend. If this process continues, an endless cycle of death and rebirth, then even in the quietest state, creation has not been silenced, only slumbering. But these ideas remain highly speculative, pushing the boundaries of our knowledge. The probabilities involved are uncertain, the mechanisms are not yet understood, and the very possibility of their existence is still debated. And even if such fluctuations do occur, they may be forever disconnected from our universe, their expansions sealed off by cosmic horizons, their timelines unreachable. To us, the parent universe remains unchanged, featureless, and without witness, existing in an eternal state of quiet equilibrium. The new bubble universe is not a continuation of our own, but an offshoot, a parallel reality sealed in its own causally separate envelope, forever beyond our reach. What emerges from nothing may not relate to anything that has come before, existing in a realm entirely independent of our own history. And so we are left with two extremes: a universe that has emptied itself into a pure, stable vacuum, a state of absolute stillness, and the faint, uncertain possibility that this vacuum contains the seeds for other realities, universes waiting to be born. Whether this represents rebirth or finality, a continuation or a conclusion, remains unknown, shrouded in the mysteries of the cosmos. What is clear is that space-time as we know it, curved by mass, shaped by light, measured by change, has vanished, fading into a state beyond our comprehension. What remains is not lifeless but formless, not cold but changeless, a state beyond temperature. It is the final abstraction of a universe that once burned with stars, a mere shadow of its former glory. Perhaps this is the true asymptote, the ultimate limit, not just of time or entropy, but of physical possibility itself. As energy disperses and structure fades, the very tools we use to describe the universe begin to lose their meaning, becoming blunt instruments in a realm beyond their reach. Physics relies on contrast, mass and emptiness, force and resistance, time and motion. When all contrast is erased, when all distinctions vanish, what remains is not a broken theory, but a theory with no subject, no phenomena to explain. The universe no longer has something to be about, no longer holds any secrets to uncover. And yet there is still wonder in this silence, a profound sense of awe in the face of the unknown, the idea that everything we know, all the stars, galaxies, thoughts, and emotions, arose from a brief span of ordered motion within a much longer sea of quiet is humbling, a reminder of our own insignificance in the grand scheme of things. It reminds us that the dynamic universe we now see, teeming with activity and vibrant with change, is but a fleeting moment, a transient episode in a much longer story, not a norm. That space-time, like life itself, may be temporary, a delicate and fragile construct, and that perhaps in the stillness beyond something waits, not something new, but the unshaped canvas from which all things once began, the source from which our universe sprang into existence. Among the many proposed endings for the universe, one stands apart for its stark simplicity and chilling inevitability: heat death. This scenario is not violent or sudden, a cataclysmic event that shatters the cosmos, does not involve a collapse into a singularity or an explosive outburst of energy. Instead, it is the quiet settling of everything into a state of maximum entropy, a cosmic equilibrium where all usable energy has been exhausted and no further work can be done. The universe continues to exist, stretching into infinity, but it no longer evolves, no longer creates, no longer changes. No new stars form, no black holes accrete matter, no atoms bind together or break apart. It is the final, irreversible equilibrium, a state of perfect stagnation. To truly understand heat death, we must return to the second law of thermodynamics, one of the most fundamental principles governing the behavior of the universe. In any closed system, such as the universe as a whole, entropy invariably increases over time. Energy spreads from concentrated forms to more diffuse ones. Heat flows from hot regions to cold ones until all regions eventually reach the same temperature, a state of thermal uniformity. When this happens on a cosmic scale, all gradients vanish, all differences are erased. Every part of the universe becomes thermally uniform, existing at the same temperature, the same density, the same energy level. The temperature may be close to absolute zero, the point where all molecular motion ceases, but not perfectly so, just cold enough that nothing meaningful moves, nothing significant happens. This state, particles still exist. Photons continue to travel through the vast emptiness, but because there are no differences in temperature or density, there is no motion that can be harnessed to create change, no potential energy that can be released to do work. No energy can be extracted to build or power systems, to fuel life or drive evolution. The universe is not destroyed. It remains a vast and empty stage, but it is done, its potential exhausted, its story finished. Time continues to pass, but without events to mark its progress, without change to define its flow. Space expands, stretching into infinity, but without consequence, without altering the fundamental state of the cosmos. Matter exists, scattered thinly throughout the void, but without interaction, without forming structures, without creating complexity. It is not emptiness, a state of complete nothingness, but stillness, a profound and absolute lack of change. Universe that has gone as far as it can go, reached the limit of its potential, and settled into an eternal slumber. This scenario does not contradict the known laws of physics. In fact, it follows directly from them. Every process we observe, from the burning of stars to the mixing of air in a room, increases entropy, contributing to the overall disorder of the universe. Given enough time, an unimaginable expanse of years, the total entropy of the universe must inevitably reach a maximum. And when it does, there is nothing more for the universe to do, no more processes to unfold, no more changes to occur. The lights go out, not from a sudden catastrophe, but from a gradual completion, from the exhaustion of all usable energy. The cosmos becomes a resting system, a vast and silent tomb, forever at peace. One of the striking features of heat death is its permanence, its irreversible nature. Once entropy is maximized, once the universe has reached its final equilibrium, it cannot spontaneously become ordered again. The arrow of time points in only one direction, and there is no turning back. There is no reverse flow of heat, no undoing of the expansion, no spontaneous emergence of order from chaos. Even if regions fluctuate briefly, as quantum theory allows, these fluctuations are limited in scale and duration, fleeting and insignificant. Nothing complex, lasting, or structured can arise again. No new universes can spring from the ruins of the old. It is a horizon beyond which no story continues, a point of no return. This vision of the end is haunting in its quietness, unsettling in its simplicity. There is no collapse, no external boundary, no dramatic moment of conclusion, just a deep stretching quiet where galaxies once burned, where particles once collided, where time once marked change. All that remains is distance, silence, and the gentle hum of equilibrium, a vast and empty cosmos at absolute rest. This version of the universe, the end is not an event but a temperature, a state of thermal uniformity. And when that temperature is everywhere, when every corner of the cosmos is at the same energy level, the universe has reached its final form, its ultimate destiny. Closely related to heat death, but often described with its own distinct name, is the scenario known as the Big Freeze. While heat death emphasizes entropy and thermodynamic equilibrium, the Big Freeze focuses on the relentless expansion and cooling of the universe, the gradual dissipation of all energy into the vast emptiness of space. It describes a cosmos that grows colder and more dilute with time, not because it runs out of energy, but because that energy becomes so spread out, so thinly distributed, that it is no longer usable, no longer capable of sustaining any form of activity. In both cases, heat death and the Big Freeze, the ultimate outcome is similar, a cold, empty, and lifeless universe. But the emphasis differs. The focus shifts from thermodynamics to cosmology. The Big Freeze begins with the same observations that support modern cosmology. Galaxies are moving apart, space is expanding, and that expansion is accelerating, driven by the mysterious force known as dark energy. If this acceleration continues unchecked, if dark energy remains constant and dominant, the distances between galaxies will grow so great that they will no longer be able to interact, their light unable to bridge the ever-widening gulf between them. Even within galaxies, stars will eventually fade and die, exhausting their fuel, and black holes will slowly evaporate, radiating away their mass in a process known as Hawking radiation. Eventually, all matter will be too far apart to exert any significant gravitational influence, drifting in isolation through the expanding void. The universe will not just be cold, it will be lonely, a vast and empty ocean with no islands in sight. This vision, the cosmos stretches indefinitely, expanding into infinity. There is no limit to how far space can expand, no barrier to halt its relentless outward march. Every particle drifts further from every other, receding into the darkness. Over time, the density of the universe drops ever closer to zero, approaching a state of perfect emptiness. Even photons, the fundamental particles of light, become so redshifted by the stretching of space that they carry almost no energy, their wavelength stretched beyond detection. Light fades, motion ceases, not because the laws of physics have changed, but because the universe has removed every condition needed to sustain motion, every source of energy to drive activity. One of the defining features of the Big Freeze is that it does not require any new physics, no exotic particles or unknown forces. It follows directly from what we already know, from the properties of dark energy, the conservation of mass energy, and the dynamics of an accelerating metric. It is a quiet prediction, not based on a dramatic endpoint or a sudden transformation, but on the continuation of current trends, a simple extrapolation of the observed behavior of the universe. If nothing interrupts the expansion, if dark energy remains constant, then the Big Freeze becomes not just likely but inevitable, a cosmic destiny we cannot escape. In contrast to heat death's focus on entropy, the Big Freeze is more about geometry, about the ever-increasing distances and the ever-decreasing density of the universe. The universe does not just cool, it becomes infinitely wide, an endless expanse of empty space. The horizon of causality collapses inward, shrinking to encompass only the immediate vicinity of each particle. Even light, which once connected distant galaxies, allowing them to communicate and interact, becomes trapped in isolated pockets of curved space, unable to escape the ever-increasing pull of dark energy. Time continues to pass, an endless flow of moments, but no signals are exchanged, no information is shared. The universe becomes a collection of disconnected regions, each drifting alone in a sea of silence, unable to influence or even perceive any other. To observers, if any could survive long enough to witness it, the Big Freeze would feel like a cosmic withdrawal, a gradual fading of reality. First, the galaxies disappear, receding into the distance until they are no longer visible. Then the stars fade, their light dimming as they exhaust their fuel. Finally, the warmth of particles becomes imperceptible, the last vestiges of energy dissipating into the void. In the end, space would feel both endless and empty, a place where the canvas stretches forever but nothing remains to draw upon it. No colors to paint, no stories to tell. And in that vast quiet, the universe would reach not a climax, a dramatic conclusion, but a drifting away, a long, cold exhale into the infinite, a silent farewell to all that once was. While if this in the but in the unlike a structure the top galaxy then in the lab even the laws nothing it depends current still and it's whether a cause it is one of the in this instead if this to under that enter the marble if a lower applied such an inside chemistry it would because the next it is not the mass this does it may never happen at all, remaining a theoretical possibility that never manifests in reality, but it remains a mathematically valid outcome lurking in the equations that describe our universe's foundations, a potential catastrophe that we cannot entirely dismiss. What makes vacuum decay so unsettling is its finality, its absolute and irreversible nature. It offers no aftermath, no debris, no future. It does not stretch space or cool matter or create new structures. It erases the stage entirely, replacing it with something else, something we cannot even begin to imagine, because we are made of the laws it would destroy, the very structures it would dismantle. And yet, despite the utter devastation it represents, this final obliteration isn't some cosmic failure, a flaw in the grand design of the universe. Instead, it's simply another potential pathway, one more way in which quantum fields might evolve and transform. It's not an ending in time, a cessation of the temporal flow, but rather a profound change in being, a metamorphosis of existence itself. Not every model of the universe's ultimate fate envisions a descent into utter silence or complete destruction. Tantalizing theories propose that our cosmos might be just one component of a far grander cycle, an eternal dance where expansion inevitably yields to collapse, and death paves the way for an astonishing rebirth. These captivating concepts fall under the broad umbrella of cyclic cosmology. Imagine a universe without a singular beginning or a definitive end. A cosmos that instead oscillates endlessly between phases of growth and contraction, perpetually rewriting itself in infinite loops of time. The earliest and perhaps most intuitive version of this idea is the Big Crunch. In this scenario, the universe's ongoing expansion gradually decelerates, eventually grinding to a halt and reversing direction. Galaxies, once hurtling away from each other, would begin to fall back, drawn together by the relentless pull of gravity. Clusters of galaxies would merge in spectacular cosmic collisions, temperatures would soar to unimaginable levels, and the entire universe would collapse inward, ultimately returning to a state of extreme density, a singularity, perhaps mirroring the conditions that birthed the Big Bang. From this infinitely compressed state, a new expansion could explode forth, giving rise to a new universe. But understand this wouldn't be a mere sequel to our current universe, a continuation of the same story. It would be a complete and utter reset, a fresh beginning forged from the ruins of the last cycle, a phoenix rising from the ashes on a cosmic scale. However, and this is a crucial caveat, our observations of dark energy and the accelerating expansion of the universe make a true Big Crunch increasingly unlikely, at least under the framework of our current understanding of physics. If dark energy continues its relentless dominance, the universe won't contract. It will simply accelerate its outward expansion forever. But the beauty of science lies in its adaptability. Other models have emerged, adapting to these new observations and proposing alternative mechanisms for cosmic renewal. Some suggest that the cosmos could still bounce, not because gravity pulls it inward, but because of deeper, more fundamental quantum or geometric processes that cause space-time itself to recycle. These versions of the theory posit that a bounce could occur even within an ever-expanding space. One such theory, known as the ekpyrotic model, paints a picture where the universe we observe is just one phase in an ongoing series of collisions between higher dimensional spaces, often referred to as branes. Each collision generates a new Big Bang, unleashing a fresh cosmos with entirely different initial conditions. Imagine two vast invisible membranes colliding with unimaginable force, each impact seeding a new universe with its own unique set of physical laws and constants. These mind-bending models time stretches infinitely in both directions. There was no first universe, and there may very well be no last. The cosmos breathes, expanding and contracting, each cycle separated by a kind of cosmic heartbeat, a rhythmic pulse that echoes across eternity. Other cyclic models focus on the idea of entropy resets. The second law of thermodynamics dictates that entropy, often described as a measure of disorder, must always increase within a closed system. Therefore, these theories propose that some mechanism, perhaps triggered at the point of collapse or during the bounce, resets the entropy level, allowing a new universe to emerge in a low entropy state, ready to evolve and complexify anew. The precise physics of such an entropy reset remains a profound mystery, potentially requiring a deeper understanding of quantum gravity or string theory to fully unravel. But if it's true, it would allow the universe to begin again without violating the known principles of thermodynamics. It's like hitting the reset button on a messy room, restoring order and allowing for new possibilities. Cyclic cosmologies are inherently attractive, not just for their inherent elegance and symmetry, but also for their ability to sidestep the apparent finality of heat death, the big freeze, the big rip, or vacuum decay. They suggest that the cosmos isn't a story with a last page, but a rhythm with no final beat, an eternal song that never truly ends. Whether through a quantum bounce, a brain collision, or a geometric reset, the universe would continually reawaken, not as a perfect repetition, but as a magnificent renewal. Each cycle would be unique, shaped by the random fluctuations and quantum uncertainties of the previous era, yet fundamentally connected to all that came before. And in this way, the universe would never truly end. It would simply begin again and again and again. After tracing so many possible futures, the cooling stillness of heat death, the infinite drift of the big freeze, the violent unraveling of the big rip, the sudden transformation of vacuum decay, and the breath-like renewal of cyclic models, we are ultimately left with a quieter, more profound question. Will the universe truly end? Or is the very concept of an end simply a human construct, a concept shaped by our limited experience and applied to something that was never meant to follow our neat patterns of beginning, middle, and end? In our ordinary lives, endings are inextricably tied to narrative. A star burns out, a book closes, a lifetime passes. But the universe may not fit so neatly into such human-centric frameworks. Time, at the largest scales, isn't a story with a beginning, middle, and end. It's a dimension, like space itself. It doesn't inherently know closure. Many of the endings we've explored are not discrete events, but rather asymptotic limits, horizons that are approached but never truly reached. The universe doesn't fall silent in a single dramatic moment. It simply becomes more quiet, more diffuse, more settled, until nothing meaningfully remains to unfold, at least from our perspective. This gradual unwinding challenges our very sense of what it means to conclude. If the cosmos still expands, still contains particles, still holds quantum fields, is that truly an end? Or is it simply a different mode of being where complexity has faded but existence in some fundamental form continues? Perhaps the universe in its later stages becomes not dead but still, not finished but featureless. The tools of physics still apply, but their subjects, the vibrant complex structures we observe today, have largely left the stage. Even in the more abrupt scenarios such as the Big Rip or vacuum decay, the word end may be profoundly misleading. These events don't necessarily destroy the idea of a universe. They simply replace one with another, a new space-time, a new geometry, a new set of physical laws and possibilities that we cannot even begin to predict or comprehend. In that sense, they aren't finalities, but rather transitions, gateways to realms beyond our current frame of reference. What ends, perhaps, isn't the universe itself, but the rules by which we once understood it. And then there's another possibility, a truly mind-bending concept, that the question of endings itself is fundamentally incomplete, that our cosmos is just a tiny part of something vastly larger, a multiverse, a deeper quantum framework, or a system of laws that generates not one reality, but an infinite array of others. In that perspective, our particular universe may end, but existence continues, not in a sequel, but in parallel. Other realms, other histories, other versions of physical law may persist, utterly independent of our own. And what feels like a profound and terrifying end here may be nothing more than a page turned in an infinite library elsewhere. In the end, or perhaps we should say, at the edge, we are left with silence, not as a cessation, but as a fundamental condition. The universe may not end in drama or collapse. It may not even end at all. It may simply evolve beyond structure, beyond change, beyond time as we currently understand it. Whether that stillness represents an ending or a threshold depends not on the stars themselves, but on the questions we choose to ask. And so, with the last of the hypothetical futures now behind us, we are ready to drift into quiet reflection. And so the stars have faded, the galaxies have wandered into darkness, and the deep fabric of space itself has stretched towards stillness. What once burned brightly now rests in silence. Not gone, not broken, only quiet. Time, having carried the universe through its bright beginning and long unfolding, slows its breath. There are no more clocks here, no pulses of light, no gravity wells or spinning clouds, only distance, only presence. The universe does not mourn its stillness. It does not need noise to be whole. It simply becomes what it must become. And perhaps in that quiet there is something beautiful, a kind of completion that does not require understanding, a kind of peace that exists without asking why. You, listening now, are part of that same long journey, made of atoms forged in stars, drifting on a planet still warm with light. And while you rest, the universe continues to unfold. Not quickly, not loudly, but with the patience of forever. So if you find yourself letting go, if your thoughts begin to drift, let them. There is no need to stay awake for the end of the universe. It has no end you can miss. It simply fades, like breath on glass, like the last ripple on a still pond, like the hush after the final word is spoken. And so, under the quiet stars, the story continues. I hope you sleep well and dream softly. Good night. Music, 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 music. Thank you. Music, 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 music. Thank you. Music, music. Thank you. Music. Heat, heat. Music, music. Thank you. Music, music. Heat, music. Heat, music, 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 music. Thank you. Music, 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 music. Heat, heat. Music, music, music. Heat, heat. Music, heat, heat. Music, music, music. Thank you. Music, 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 music. Heat, heat. Music, heat, heat. Music, 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 music. Thank you. Music, 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 music. Heat, heat. Music, music,